This is the Lab 6 Prelab for analog electronics. And this lab is focusing on a two-stage CMOS amplifier. The first stage is the same as the previous lab. It's a differential pair with an active load. And the new stage that we're adding is a common source transistor, PMOS M7, with a load of RD. Also driving a capacitively coupled output load RL. And so we're trying to understand how two stages interact together to give you more gain, basically. And the premise here is that the total gain of the amplifier, AVT, is equal to AV1 times AV2, where AV1 is the gain of the first stage, which we analyzed in the previous lab, and AV2 is the gain of the second stage, which we're adding for this lab, M7 and RD with RL. So this pre-lab starts with the design. It says choose RF so that the differential amplifier is biased with 4 milliamps. We've already done this. This was basically the premise of lab 4. So RF is equal to same as lab 4 and 5. And if you already have this circuit built from the previous labs, then you're good to go basically from here over. We're just going to add this new stage here, which will be different. The next part is to determine the current flowing through M7 and RD. This might take a little bit of thinking here, but keep in mind that M3, M4, M7 are all PMOS. They all have the same WL, KP prime. And if you take a look here, if everything is matched well here between M3 and M4, then VGS and VDS will be the same. VGS is the same because they have the gates connected together and the sources are connected to VDD. So as long as everything is matched, the drain voltages will also match. And so this gate voltage here will be the same as the VDS voltage here, and which sets the gate voltage and VGS of M7. So if everything is matched well, ID3 is equal to ID4, and that will also equal ID7. But keep in mind that there was 4 milliamps here, which means 2 milliamps goes to each side here. So M3 and M4 were 2 milliamps. That's also going to basically be mirrored to M7, and that's also going to carry 2 milliamps, which means there's also 2 milliamps flowing through RD at DC. And that assumes very good matching between these three transistors. You'll find in the lab that that's not entirely true because each chip only has 2 PMOS and 2 NMOS. So it's hard to get 3 PMOSs to match because you have to use 2 separate chips. And so you'll find that the current isn't exactly matched all the way. But it'll be as good as we can get. Alright, the next part is to determine the DC output voltage at the node between RD. Oh, you have to design so that the voltage is 0 volts. So we want to make this voltage pretty close to 0 so that we can swing high and low, kind of like in the common emitter lab. We need that to be able to swing as high as it can in both directions. So if we get this close to 0, that means we can swing high pretty far, swing low pretty far, because we've centered the output between the two rails, +5 and -5 volts. So we can just use Ohm's law here, which is pretty simple. So 0 volts minus VSS is equal to 2 milliamps times RD, and solve for RD. Easy as that. Keep in mind that if you round here, when you get hardware components, that your DC voltage at the output will shift because it's directly related to what that output voltage is, the resistance is. Okay, determine the voltage gain of the second stage, and don't forget to include RL. So, common source amplifier basically behaves similar to the differential amplifier. So AV2 is equal to minus GM7 because it's an inverting stage, RO7 parallel RD parallel RL, and GM7 is equal to square root 2 KP prime W over L ID7 square root of 2K ID, where ID7 is 2 milliamps, and the other values are given to you in the lab document. And RO7 is 1 over lambda P ID7, and lambda P is given to you in the Prelab doc. So with that, you can calculate AV2, and it'll be negative quantity because it's an inverting amplifier. Part 5 asks you to determine the total voltage gain of the two-stage amplifier. So as I stated before, total gain is gain of the first stage times the gain of the second stage. First stage, you figured out the gain in the previous lab. So that's from lab 5. And AV2 you just solved. So you can get the total gain from those two numbers just multiplying. It's important to note that the gain of cascading stages doesn't add together, it multiplies together. And that's it. So the next part says calculate the minimum value of VCOM that is needed to ensure proper operation of the differential amplifier. You did this for lab 5 already. It's just here basically to note that there's a minimum value at the inputs before you drive M6 into triode. So you can refer back to your notes about the differential amplifier from lab 5 and you'll understand why there's a minimum voltage at the input. And then you're asked to run a simulation to verify your calculations here. Make sure that those make sense. That one's not too bad. And the last part is describe how you would modify this circuit to increase the voltage gain while keeping V out close to 0 volts DC. So if we look at this circuit, there's not really much we can modify here. All the transistors, you can't change the modeling parameters. You can't change W over L like you would in a real IC design. All you can change are RF and RD. And we want to increase the voltage gain. So consider what you would have to do to these two in order to increase the voltage gain while also keeping the output close to 0 volts. You'll have to resize the resistor and the reference resistor in order to change the bias current. And once you change the bias current, you'd also have to modify RD in order to keep the output close to 0. But what direction would you have to change RF? Would you have to increase it or decrease it? And just describe what you would have to do to RD in order to keep the output close to 0. And that's it. So the next part of this assignment is the transient simulation, just to show that the gain is roughly what we calculated it to be.